Hi everyone. Today we're going to go over atomic level kinetics, and we're going to tie into that thinking about kinetics in terms of enthalpy diagrams. So at the atomic level, when we're thinking about kinetics, we're thinking about what is it about the way atoms interact that lead to chemical reactions. And one of the best ways to do this is to take a look at a simulation. So we're going to take a look at this sim. You can get to this yourself. It's on the website called PHET, P-H-E-T, .colorado.edu. The easiest thing to do is just type in PHET reactions and rates into Google or your favorite search engine, and it'll take you here. It has this slightly funny compatibility issue. You have to run it using something called ChirpJ or something. Anyway, so just give this one a try. It's really worth staring at it for a little while to get some ideas. Okay, so for one thing, so what we've got going on here is there's a reaction that could take place between the yellow atoms, A. You'll notice down the lower left-hand corner here, there's a reaction. The atoms A can react with the molecule BC to produce the molecule AB and the atom C. So basically, A comes in, kicks out C. But you'll notice from looking at the simulation itself that we have lots of collisions happening. And you would think that after at least a few collisions, you might have a reaction, right? You might think that if this happens by atom A jumping in and kicking out atom C, that a certain number of collisions would result in a reaction. It turns out that most collisions are unsuccessful. There's a couple of reasons for this. One of them is that it actually has to happen in the right orientation. The reasons for that are a little beyond the scale of this course. We'll talk more about that when we get to, or when you get to organic chemistry. So that's next year. But the other reason is there has to be enough energy for a reaction to happen. So the way we, in particular kinetic energy, the molecules have to be moving fast enough that when they run into each other, there's the chance that that bond between B and C can get broken as the bond between A and B is starting to form. The only way we have to change the energetics here is to raise the temperature. So the energetics are determined by lots of things that you don't have to worry about really, but the only way here to change the rate of this reaction at the moment is to increase the temperature. So on the sim here, I'm going to add a lot of heat, and you'll notice that the molecules are now, oh, there you go. So the molecules are moving much faster, and we finally have a reaction. We finally kicked out that, that C atom as the energy of the reactions, or the kinetic energy of the particles in the reaction has increased a lot, all right? And so now the particles will go back to doing their thing and bouncing around, and the reaction's over. Another thing in this sim, and we didn't emphasize this much in class, another thing you can do here, let's reset this. Yes, I want to reset. One thing that we can do here is we can just flood this reaction with lots and lots. Oh, good. It didn't like that. So we can flood the reaction with lots of the of one of the reactants, and we'll get a much faster reaction. So this is over here on the mini collisions. So instead of 10, we can do 20. All right. And now we've increased. We can increase the rate by increasing the number of collisions, and then somewhere in there there'll be a successful collision, and there's a greater chance of that simply because there's more collisions. There we go. All right. So that's two ways that we can increase the rate here. We can raise the temperature, and we can raise the number of collisions. We can raise the temperature, which raises the kinetic energy of the particles, and that's going to make it more likely to break some bonds. We can also increase the number of particles that are involved, and that's also going to increase the chance that one of those collisions will be successful just because there's more collisions. Okay? All right. So most collisions don't result in a reaction. Like, that's the first thing here, okay? Is that, and this is really true at the atomic level. Like, most reactions aren't, most collisions don't successfully result in a reaction. For a collision to be successful, it has to have the correct orientation and the correct kinetic energy. In other words, the energy of the collision has to be strong enough to break, or at least start to break, a bond. All right, and we know from earlier discussions that bond breaking is endothermic. That means energy has to be absorbed. All right, so anytime you're breaking bonds, energy is going to have to be absorbed. And the way we're going to think about that is we're going to draw that in terms of an enthalpy diagram. All right, so we looked at these earlier in the semester when we were talking about delta H, but we drew them much simpler. We were just saying, like, here's the enthalpy of the reactants, here's the enthalpy of the products. If you have to go down to get from reactants to products, the delta H is negative, and that's exothermic. All right, so here we're doing a little more. So the reactants are still shown over here on the left, the products are shown over here on the right. So if you kind of draw a line to help you see it, the delta H is still shown here, and this is a negative delta H. All right, so we have an exothermic reaction, but to get from reactants to products, we have to go through something called the transition state. And the energy, this is the energy of the transition state. The details of the transition state are super beyond the scale of this class, and you don't have to worry about it, but know that something has to happen for you to start to break bonds. That's the key thing here. We're starting to, or we are actually breaking a bond before the reaction can happen, and that is going to be an endothermic process. So that's always going to have a positive delta H, all right? And that endothermic process of starting to break some bonds has a specific name when we're talking about the energy difference between the reactants and the transition state, and that's known as the activation energy. And we abbreviate that E sub A. So the activation energy is always going to be endothermic because it's starting to break some bonds, or actually is breaking a bond, and that's always going to require an input of energy, all right? So we always see, going from reactants to products, there's some, in the enthalpy diagram, there's always this hill in between them that is going to require some input of energy. And that's the origin of the fact that not all those collisions we looked at in the sim were successful, right? And they became more successful when we were putting more energy in, because more of those collisions would have had enough energy to meet this activation energy requirement, to have a reactant come in with enough energy to break a bond, all right? Okay, so one quick note, these diagrams have this goofy reaction coordinate x-axis. Don't worry too much about what it is. Just think of it as like progress of the reaction, right? And that's, in other words, you're starting out in reactants over here, and over time you're going towards things turning into products, all right? So don't stress too much about that axis. All right, anyway, I want you to pause the video and try this practice problem. I'd like you to draw an enthalpy diagram for a reaction that's endothermic and slow, and exothermic fast, and which one of these would correspond to wood burning. One thing I guess I didn't say is the bigger the activation energy, the slower the reaction will go, because fewer molecules have enough energy to react, okay? So when we talk about, so I'm kind of giving this away, when we talk about a slow reaction, we want a large activation barrier, okay? A large activation energy. So go ahead and pause the video, draw those on your own paper, then restart and I'll go over it. Okay, for A, we're looking for a reaction that's endothermic, so we got to start the reactants down here and the products have got to end up here, right? Because that way we'll have a positive delta H. All right, and then we've got to have a activation energy here, and so this is going to represent our E sub A, our activation energy. Oh, and we said it was going to be slow, so let's make this peak a little higher. There we go. That'll be really slow. Big activation energy. All right, and then the part B. Oh, I just realized part C doesn't make any sense. I'm sorry. Just if you were stuck on part C, just ignore me because none of these correspond to wood burning. I'll go over wood burning real fast. Okay, exothermic. So we're going to have reactants up here. We're going to have products down here, and it's going to be fast. So we're going to have a small activation energy. All right. So your activation energy. That's our E sub A. It's really small. All right, and you have a big delta. Oops. You have a big delta H that's negative. All right. Wood burning would have would be exothermic and slow, right? I mean, I guess it could be. It's fast once you get it burning, I guess. But it has a high activation energy that requires the input of something like a match to get going. All right. So there you would have you'd want to have an very exothermic reaction with a big activation energy to it, right? Because you can't get a fire started without lighting it on fire. All right. Sorry about that. I apologize for the confusion. All right. Please leave any comments or get in touch with any questions. And I hope this was helpful. See you soon.